Recently we've been building some buck converters and boost converters and so on using some larger chips which could provide higher amperage power, but quite often in projects we will want to use small microcontrollers and we want to run them off a single lithium ion cell, and these lithium ion cells, they tend to produce about 3.7 volts, but they can go right down to 3 volts, or they could even go up to 4.2 volts when they are fully charged. But we need 5 volts for most sensors and microcontrollers to run circuits. So it would seem to be convenient if we could create a little boost circuit that actually could take input from a lithium ion cell and provide us with 5 volts for our microcontrollers and other circuits, sensors. So in looking around, I found a very cheap supply of these little controllers, MT3608, and it seems to need very few components. A small inductor, 22 microhenries, a Schottky diode, a couple of resistors, and a few capacitors. Now, I've previously done a little bit of testing with these things, and I really think that the circuit, this part of the circuit here is basically based on the data sheet, which we'll have a look at, and there's still quite a bit of noise coming out of this thing, so I have put space on my little board for an extra inductor and a larger capacitor to filter out some more of the noise. So we're going to be building that, and we're going to be looking at, first of all, what it outputs without those two components, and then we will add those and see what the differences are. So this is a temporary little board that I have created just for testing. This is by no means anything that's final for production or anything. We just want to see if the circuit works. And this particular circuit, I did not put a fuse or anything on there. I would normally want to add one of those PPTC, whatever they're called, fuses, or just an ordinary glass fuse or whatever, to make sure that the circuit never gets to try to output too much current. This particular little chip here apparently can handle up to a couple of amps, but I designed this circuit to do about half an amp, because that is more than enough for most of the small microcontroller circuits, and it also makes the components a lot smaller. Now this is the data sheet for the MT3608, and it says it's a high efficiency 1.2 megahertz 2 amp step up control converter, and 2 volts to 24 volts input voltage, which is what we want, because a lithium ion cell, when it is close to being fully discharged, will be somewhere like 2.9 to 3 volts. So this is well within that range, and up to 28 volt output voltage, but we only really want 5 volts for our usage. And here is a typical application, and you'll find that the only difference is I put a trim pot there just for testing, so we can adjust the voltage slightly. In a finished circuit it would be fine to use 2 resistors there and to get a voltage between 4.95 and 5.1 volts or something like that. And we are not going to use the enable pin, we just hook that up to the input voltage so it's always on. So that's basically it. It's an SOT23 package. It's very tiny, and well, that's really, there's more information there, but that's really all we need to know right now. It has a MOSFET built in, so that is a good thing. We don't have to hook anything up externally. So I found this thing on the LCSC website. I've been buying components from them recently. I've had bad experiences buying components on AliExpress, but I found that LCSC is it's a, I think they're Chinese or Asian, wherever they are located, and their components seem to be good, and they seem to be working, and they have good, you can order something and usually takes only about a week or so before you get them. And as you can see, this one here, this component was about 9 cents each, and I bought 5 of them to test them out. It cost me 43 cents. I did also buy some other components there, as you can see. The TPS, or the TP5400, is supposed to be a one-chip solution. It has battery management as well as like a boost converter built in. We'll be looking at that in another video, see how that might work. And then these 3 chips over here, DW01A, TP4056 and 8205A, these are the 3 chips you will find on one of those little battery management boards that you can buy on AliExpress and so on. We'll have a quick look at that so you can see, but in future I might decide to use some of these chips on some circuits. I'm not sure, but right now the little boards are so cheap with these components already on them that it doesn't seem to be a worthwhile project. But I thought I would buy some of these components. Good to have them in stock. Maybe I need to replace some sometime and so on. So where I got the idea from is I got these little tiny microcontrollers. I got an ESP32, and this is a RP2040 based device, and sometimes I want to make little projects that are very small, and these are very small boards, but they will need some power, and I would be wanting to run them off a lithium-ion cell. So that's where I got the idea, in order to make a little circuit that we could add to it. Now when it comes to buck converters and boost converters, you'll find them everywhere. Like this is an old modem board, a DSL modem board for Motorola, and you'll see this little island over here, and this is actually a buck converter, probably 3.3 volts or something like that for some of the components on there. And this particular chip here is actually, as you saw, the one that we are going to be using is actually made for boosting voltage, but there are others, of course, that are made for dropping the voltage, or like a voltage regulation, which we call a buck converter. And that particular one we're looking at also was using a SOT23 chip on there, and this is the one that is actually there, an LT1933, 600 milliamps, 500 kilohertz, step down switching regulator, So you will find those things everywhere. This is a circuit that's roughly that it is based on. So it's good to know about these things, and that's why I have been looking at those and building some test circuits and what have you to see what they're all about. So here again is that little section there with the buck converter on it under the microscope. And if we look at it from a longer distance, you'll see how it is just like a little island there. Yeah, so there it is there. Yeah, that's a little thing. Now you'll notice that when we were building this circuit, we're also going to be using a small inductor like that, which is good for less than an amp. If you were going to create a circuit with multiple amps of, you have to use a bigger inductor like that one, for instance. But we are not doing that. We don't have a need for more than half an amp, as I said, and that's all we'll be doing and testing it at. So here is our little board that we are going to be building, and as you can see, this is the actual little controller here. It is absolutely tiny. If I put it on my finger, you see how small it is, and it has to go over here on this board. And it's going to be tricky to solder, I'm sure, so we're going to be using this very fine solder tip here to do that. Okay, so the first thing we're going to be doing is soldering on this capacitor over here, and I actually designed the board in order to take that true hole tantalum capacitor, but I found this thing afterwards, but I think we can get away with it by soldering it on over here. And the reason I'm going to do this one first is that I can solder it on, and then I can use a multimeter and double check that, you know, there's no bridging or something, and that it is making an appropriate connection there. That's what I'm thinking it will go, and this area should be wide enough to solder it on, but I want to make sure that there's no solder going to be ending up underneath, you know, touching that, and I'll be able to test that with a multimeter. If this is the first component that I'm soldering on, then I can test that very easily. There won't be any interference from others. So let's have a look. Let's put on some flux over here, and let's get some solder. Turn on the soldering iron. I'll use the bigger soldering iron first, just for this one here, and then I will swap this one out and go to the 50 watt one. This is the 130 watt one. Right. Notice that I've put some little markings on the board. You'll see later on, like there's a plus sign over here. Reminds me that that's the positive side, and the diode here may not be that easy to see right now, and also where pin 0 is on the chip, which we'll see later on. Okay, so let's get my special tweezers here. These guys here are actually, they clamp on without you having to squeeze them, which I find important when I am soldering with my right hand. I don't want to be concentrating on my left hand squeezing things, because then usually they snap out of these tweezers, and then it is not working too good. I'm going to turn this around so that I can get to it from the right hand side with this soldering iron. That'll make it a bit easier. So hold on. Okay, there you go. I have to look at it under the microscope. Okay, that's making a good connection. I think I can get the other side here. It's always a little bit more awkward when you're soldering under the microscope to make videos, because you want the video to be able to see what's going on, and it may not be exactly in sight. Alright, so I'm just going to get the multimeter now quickly and take some reading. Okay, all is well. The capacitor is making a good connection, and we are in business. So let's have a look now. Okay, so we've got to put this little chip in place. This is not going to be easy because it is absolutely tiny. So this is where pin 1's got to be, and that little dot there is pin 1. So we're going to have to use this tiny little tip here. You're going to need flux. Now the purpose of this flux is not so much to make things stick like some fluxes to get corrosion off and stuff like that, and to stop oxidization, but this particular flux, this MTech stuff, is if you can see it there, is MTech. It actually allows the solder to stop it from making bridges. It will I don't know if it's not capillary, actually, the surface tension or something underneath the flux causes it to it helps against that. This one here is actually connected to a fairly large. I'm going to try to get that one pin soldered on so that it won't be moving around anymore. And I've got to do this while I look at the microscope, and unfortunately my screen is actually to the right, not in front of me. That all makes it a little bit harder, but we will manage. Okay. You couldn't do this without a microscope. It is just those little pins are too small. Okay, so I think that does that one. And this is a ground pin, and that is a control pin. Now let me have a look here. Do I need to move that over, or no? I think that is good. And those two pins are actually connected together at the top, and this bottom pin here is not connected to anything. It's just actually, so it's not a very important one. Let me try to get the top one there. So now let me get some of the other components ready. Okay, so how I do this is that I put the circuit, the board view from KiCad on the screen, and then I can see where the actual components go, like, you know, C5 over here, and I can vary the, I can turn off the traces if I want to. You can do all that stuff, and you can stop the background. So in various modes, so I can see, you know, C3 is 100 nanofarads, R7 is 2.2K, so I can see where they go on the actual board. If you're wondering how, because it can be tricky, because when you make your own boards and you don't put like solder mask or anything on it, sometimes it can be confusing where things go. So that's just how I do that. Alright, so let's go and do this little capacitor that goes over here. You know, I just want to try some of that. I've got some other, or maybe that camera there will work. I've got some of this flux here, soldering paste. I'm wondering. Yeah, it actually works a lot better. I think my other flux is getting old. All right. Okay, that's one. Now, the next one. Actually, I think it's time to try to put this little, how does that go? Yeah, I'll put a little L there. See that an inductor goes there, and it is this one here. Has to go over there like so. Now these little inductors, they don't really have much overhang, but we will try. Okay. Put a little bit on there. Now try to do the other side here. Now I can put a little bit more solder on there. I believe that will do it. Feels pretty solid. Okay, and now we need to put on this diode. I think I'll move it over just a weeny bit. Do it. Well, I think I will solder up the little wires and the battery holder of camera, and then we're actually going to be ready for testing. Okay, I've got the little board connected up, and we do not have the final output filtering installed because I wanted to have a look at how well this works just with the standard circuit as it is outlined in the data sheet. I have an electronic load connected, as you can see at the top right there, and I've got the multimeter connected on, as you can see, on the top left, but I might be moving that to the bottom right because next we are going to bring up the oscilloscope. Right, so first thing to do is to set up the oscilloscope for measuring a ripple. And the first thing that we will do is to change the coupling to AC. I'm going to mouse connector to the oscilloscope so you can see what I'm doing. When you measure ripple, you always select 20 megahertz bandwidth. That is traditional. And then we want to analyze, and we want the power analyzer, and we want ripple, and we want to have the display. Put it out of the way there. And we might even, no, I think that'll do it. Okay, things are turned off and we've got 10 millivolts of ripple without any power applied, so this is just noise, I guess. Okay, we have power applied, and let's have a look now. Okay, and this is 300 milliamps of power we're drawing now. Okay, let me fiddle with the doesn't look good, does it? Let me fiddle with the okay, that looks pretty nasty. So I think I'm going to put on the extra filtering now, the extra inductor and the capacitor, and see where we go from there. I suspected as much. I mean, as far as the multimeter is concerned, it is 5.13 volts, but it has got really way too much ripple there. Just reset it to statistics, so it's like 0.6 over 0.6 volts out of the 5, so that's like more than 10%. That will not do. Okay, so let me solder on those extra components and see what happens. Okay, this is at 100 milliamps, 70 something millivolts. It's not very good, and of course the frequency it seems to be having like 3.5 megahertz or something. So I think I'll have to do a little bit more experimentation here and find out what's going on. Maybe just getting some feedback or something. So I'll have to go and do some more work off camera, and I'll let you know what I find. I'm starting to wonder about these little SOT23 converters. I decided to have a look at the an existing little board that I have. It's actually a battery controller with a boost converter on it, and if you look at the little chip on there, it's got B62801 on it, and I have not been able to find out what kind of chip that is. It's obviously not the same as the one we're using, because the ground pin is on pin 1 and now the ground pin is on pin 2, and in actual fact it is actually behaving worse than the one that I built. This is what I'm getting at just 100 milliamps draw. It's regulating okay. It's got 5.5 volts. Once I draw 300 milliamps it goes down to 4.98, but you know, that's acceptable. And it has 234 millivolts ripple, and as you can see it is quite a lot of high frequency stuff there. So that begs the question if you can get rid of that by actually, if you had to use a circuit like this, could you boost the voltage to, let's say, 7 volts and put a 5-volt linear regulator on there with a couple of capacitors? What would that do? Let's try that next and see if that would work. Actually, this is with drawing 300 milliamps, and now it has 385 millivolts of ripple. It is actually quite nasty. So the circuit we built actually is better than that. But anyway, as I said, let's try. I just want to show that. Let's try it with a linear regulator attached. Hey, so I hooked up a linear 7805 regulator and a couple of capacitors, and we have on the output 5.15 volts. We're currently actually drawing 300 milliamps, and on the inputs we have 8.5 volts roughly that I have set this controller to, and it certainly has improved the situation. This is what we're getting now, roughly 65 millivolts ripple, those little pulses over here, and it's very hard to get rid of that high frequency stuff from when the square waves in the pulse width modulation thing switches. But for most purposes this would work, but you can see why you don't see these kind of boost regulators or buck boost regulators in audio circuits or other circuits that are very sensitive to ripple on the power supply, because that's about as good as it gets, I think. So it's been an interesting experiment to have a look at how these things go. The one that I built started to misbehave. I guess I've been fiddling so much and changing voltages and what have you, the little chip on there got tired, and at the last few tests that I wanted to do, as soon as I drew some current from it, it would go down to 3.6 volts instead of 5 volts, so I gave up on it actually. It may well be that if I had hooked up this linear regulator to my little board that I might have had a slightly better result than this, but nevertheless it has been an interesting experiment, and in future I might have a look if I can find some other chips that are better than these cheap Chinese ones and so on. And I think that is probably all that I can do for this episode, so I will see you guys later. If you like these kind of experiments, then please subscribe and push the little bell button and like and whatever there is there. and I'll see you guys later. Bye bye.